Alright, so as I said at the end of the last video, 9.3 is all about absolute value inequalities. So these are by definition going to be compound inequalities. So we're combining basically what we looked at 9.1 and 9.2 into one kind of concept here. And we only have one objective, just like the last time, that's to solve absolute value inequalities. So let's define absolute value inequality. So if A is a positive real number, same clause as we saw in 9.2, then the absolute value of something, capital X, any expression, being less than A, is equivalent to the absolute value, or I'm sorry, not absolute value anymore, is equivalent to negative A less than that expression less than A. And the absolute value of X being greater than that positive number is equivalent to X, that expression, being less than negative A, or X being greater than A. So I want to kind of talk about why this is, because this is usually a hang-up for students of why does it work this way? And to do that, we have to look at what the, I don't want to say true, but what the more high-level definition of absolute value is. So most of us know absolute value, as we talked about in the last section. It just gives you the positive version of whatever is inside. So if you have the absolute value of a positive, it spits out the same thing. If you have absolute value of a negative, it gives you the positive version. But what the absolute value actually talks about is the distance, a specific distance. And that is the distance from 0. So distances can't be negative. If you look at from negative A to 0, the distance to go from one to the other is still equal to A. So the absolute value of negative A, that distance is still equal to A. And this is what the higher level version of what absolute value actually does. So when we say that the absolute value of X is less than A, we're saying that the distance from whatever this expression is to 0 sits somewhere in here. X would be here. And we look at this distance. Well, this distance being less than A says nothing about where we are relative to 0, to the right or to the left. So we could also be over here at the negative thing. Either case, this distance is X and X, or I should say absolute value of X. So that's why these inequalities work this way. So if we have absolute value of X is greater than 0, or greater than A, that means, let's use a different variable, let's use W. That doesn't look like a W anymore. I promise it's a W. That means our distance to 0 of W sits somewhere over here, or alternatively somewhere over here. And so that means we are either less than negative A, or we are greater than A, because we need to be outside. So that's why our inequalities work this way. So let's look at solving some inequalities now. First one is the absolute value of M-6 is less than 2. So we split this using our new equivalency to M-6 less than 2 and greater than negative 2. And then we solve like we did back in section 9.1. So we're going to add 6 to all three pieces. We're going to have 4 is less than M is less than 8. And if you've done this correctly, you should get a true statement. When you end up with non-true statements, that's when you know you've run into an issue. So as an interval, this is 4 to 8. And on the number line, if we were to graph this, if we have 4 here, and then 5, 6, 7, 8 here, we'd have a parenthesis and a parenthesis, and that would be our solution. So moving into our next example here, this is again similar to some of the problems we saw in 9.2. we need to first get our absolute value expression alone. So I'm going to subtract 1 from both sides. The absolute value of 5x plus 1 is less than or equal to 9. Now we can, oh, we didn't mention this, but these rules are interchangeable with the less than or equal to or greater than or equal to versions as well. So we can split this into its equivalency, or change it into its equivalence, less than or equal to 9, greater than or equal to -9, minus 1 from all three pieces. I'm going to do this up here. We have -10, less than or equal to 5x, less than or equal to 8. Divide everything by 5. That gives us -2, less than or equal to x, less than or equal to 8/5. So our interval solution is -2 up to 8/5 in brackets. And on the number line, if we put our 0 here, -2 is there. 8/5 is a little bit more than 2, or a little bit less than 2. So that would be, if this is 2, be about right here, be 8/5. And our solution would be in between those. And then one more here doing the less than version. So this one is already set up. We can go straight to the equivalent version, 2x minus 1/10 less than -13, greater than 13. Now, you should notice something weird here. If you take this middle part out, we are saying 13 is less than -13. And that's obviously not the case. So it comes back to this value being a negative. Remember, absolute value of any expression is always greater than or equal to 0 because it gives you positive versions. So there's no way for the absolute value to be less than a negative or less than 0. So this tells us this is no solution, because it will never be the case where the absolute value is less than a negative or equal to a negative, as we saw in the last section. So if we flip the page again, we have absolute value of 3 times quantity x minus 2 over 5 is less than or equal to 0. Now this actually is still okay, because it could be equal to 0. Our absolute value could be equal to 0, which means we continue on. 3 over x minus 2 over 5 less than or equal to 0 or greater than or equal to 0. And just to reiterate here, because I don't want to gloss over this too quickly, if this was absolute value of 3x minus 2 over 5 is less than 0, this would be no solution, because we can't be less than 0. But since we have the equal to here, you are allowed to be equal to 0 as an absolute value, because the absolute value of 0 is 0. So we still go through the process of solving this. Now you'll see something very interesting that happens. So the first thing we're going to do is multiply everything by 5 to get rid of that fraction. 0 times anything is 0, so this is 0 less than or equal to 3 times x minus 2, less than or equal to 0 again. We divide everything by 3 to get x minus 2 is less than or equal to 0, greater than or equal to 0. And then we add 2 to every piece. And we have 2 is less than or equal to x is less than or equal to 2. So if you can be at most 2 and at least 2, that means the only choice is x equals 2. So this is actually a really famous result in math. There's a whole theorem about it if you ever go on to calculus that you study, that if you can bound, this is called bounding by the same value, you can force it to be equal to that value, because we can, if we're less than or equal to 2 but also greater than or equal to 2, then the less than and the greater than don't actually matter, and you're just equal to 2. And so this doesn't have an interval solution, it just has a point solution, a value. Again though, don't mistake this version. This has no solution because it's strictly less than 0. this does have a solution because it has the equality allowed for. Okay, so let's switch gears here out of the less than or equal to and start looking at some greater than examples. So y plus 4 is greater than or equal to 6. So according to our equivalency, this is the expression less than negative, whatever that is on the right, or the expression greater than the positive. So we have y plus 4 can be less than or equal to negative 6, or y plus 4 can be greater than or equal to positive 6. And then we solve these like we have been. Minus 4 all the way across. Y is greater than or equal to 2. Y is less than or equal to negative 10. So we have our two inequalities. This is negative infinity up to negative 10 with a bracket. It's an or, so that translates to union. And this is with a bracket 2 up to infinity. And our graph, if our 0 is here and 2 is here, we'll say 10 is right there. Negative 10. This gets a bracket here and goes to the right. This gets a bracket here. I'm sorry, I said right. It goes to the left. And this one goes to the right. So that's our graphical solution. And remember, when you have two intervals, two sets that don't touch, as long as it's a union, that's okay. When it's an intersection, an and, then this would be no solution. But since this is an or, we're allowed to have, remember, this is called disjointed intervals. So on the next example, first we're going to get our absolute value alone by subtracting 5. The absolute value of 2x plus 9 is greater than negative 2. Now some of you might be saying, oh, should this be no solution because there's a negative over here? And the answer is not necessarily, because we are allowed to be bigger than negative 2. This can still work, because what's bigger than negative 2? All the positive numbers. So the absolute value of anything is always greater than negative 2. So now we just want to see what interval of x's actually fit into here. And so we can split this into our two versions. 2x plus 9 is greater than negative 2, or 2x plus 9 is less than positive 2. And this is the positive because it should be less than the negative version of what's sitting right here. So minus 9 from both sides. And we get 2x is greater than negative 11. Minus 9 from both sides. 2x is less than negative 7. Divide everything by 2. And we get x is greater than negative 11 over 2, or x is less than negative 7 over 2. As intervals, this is up to negative 7 over 2, down to negative infinity, unioned with negative 11 over 2 up to infinity. And as an interval, negative 7 over 2 is a little bit more than negative 3. Negative 11 over 2 is a little bit more than negative 5. So if I put negative 3 here, negative 5 here, I have this for negative 11 over 2 going this way, and I have this going this way. And so what we see here is that this is actually negative infinity to infinity. Or if you remember from last section, or from the first section of this chapter, all real numbers. So you might be looking at this and going, that's weird. But remember, all we're saying is that an absolute value of something is bigger than -2. Well, every absolute value of any value that we get out of this is going to be positive, or at least equal to 0. So no matter what we pick here, we will always be bigger than -2, because the absolute value of anything is greater than 0. So whenever you get an absolute value greater than a negative, the answer is going to not necessarily be all reals, because sometimes you have to hit a certain value, but a lot of things are going to be bigger than the negative. And I would say 99% of the time it's all real numbers. You still want to go through your steps to solve to make sure that it works out correctly. So this is another unique case like the one we saw on the first side of this page. So let's move on to our last one here. We're going to get our absolute value alone by adding 9. So we got absolute value x minus 7 over 2 plus 11 is greater than or equal to 23. So this is just a standard greater than or equal to, has the same rules as greater than. So this means x minus 7 over 2 plus 11 is greater than or equal to 23, or x minus 7 over 2 plus 11 is less than or equal to -23. So what I'm going to do here is multiply everything by 2 to just get rid of the fraction right now. So that's going to be x minus 7 plus 22 is greater than or equal to 23. X minus 7 plus 22 is less than or equal to negative, oops, this should be 46. This is -46. X minus 7 plus 22 is x plus 15, greater than or equal to 46. This is x plus 15, less than or equal to -46. Subtract 15 from both sides here, and we get x is less than or equal to negative, this would be 61. And this minus 15, running out of space. Let's stick it right here. This would be x is greater than or equal to 31. And this is an or. So we have, I'm going to write it up here, our final answers. X greater than or equal to 31, or x less than or equal to -61. Excuse me. So as intervals, -infinity comes up to -61, because that's the small one, with a bracket, and since it's an or, it's a union, and then bracket 31 up to positive infinity. On the number line, if our 0 is here, and I put 31 here, and then we'll have -61 here, we have a bracket at -61 turn that way, bracket at 31 turn that way. This goes to the right, and this one goes to the left. And again, since it's a union, it's an or, we're allowed to have these untouching or disjoint intervals as solutions. So that's absolute value inequalities. In the final section, we will be looking at combining chapter 4 with inequalities and looking at systems of inequalities.